So, in the last class we have discussed about flow between parallel plates bounded by porous packing, okay, and then flow inside a tube filled with porous packing. So, as an extension of the study, we would like to study composite porous channel. So, that is channels that are partially filled with porous material. So, even these are also has a lot of applications. As a simple case, I mean not as a channel, but you can see. So, if you have a subsurface, that is like there is a porous bed and then a layer of a fluid. Okay. So, then maybe there is a packing which is just controlling the top flow, okay, like a tank. So, then you can have such a composite filled channel, and also there are some filtration techniques like you have some liquid, then you have a porous packings, and then we would like to filter. Okay. So, such scenarios. So, these are some examples, not very precise, but approximate sense. In any case, we have to discuss some elementary applications, so that we really move on to exact application. So, the first case that we are going to discuss is a composite porous channel. So, the configuration is as follows. So, this is a porous media. So, you have two plates located at minus h and h, and then we are having a interface at y equal to 0. So, this is a symmetric. Okay. So, one can really have different porous fraction. So, that is need not be symmetric. So, you can have some porous fraction of some thickness. So, and then control. Okay. So, that is possible, but in this case for simplicity we are considering a symmetric. So, this is a fluid layer. So, in the previous case we have complete porous packing. So, we had to use only the no slip, but in this case, so you have a fluid porous interaction. So, therefore, we expect the interface play a vital role. So, there should be flow transfer happening across this interface, so as the momentum transfer. So, we would like to study the impact of this momentum transfer across the interface. And mind you, we are not discussing a deformable porous media. So, in the previous case as well, it is a rigid porous matrix. In this case in particular, the porous matrix is rigid. So, we are not discussing that neither the boundary nor the porous packing inside deforms. Okay. So, that is a major assumption. Okay. So, if you formulate the problem, again one can go for a simple case of unidirectional approximation and then analyze. So, the governing equations, we define the zones as fluid region and porous region. So, in the fluid region we have equation of continuity, and then this is the momentum equation, which is nothing but the Stokes equation, and we are using the superscript f to denote all the flow quantities in the fluid domain. Okay. So, mu is the dynamic viscosity of the fluid, and coming to the porous region, we have again equation of continuity, and then we are using Brinkman equation. Okay. So, as I indicated, we are using the superscript p. Okay. And already we have discussed this is the effect of viscosity. Okay. So, now we go for the unidirectional assumption. So, that is flow is along a x direction. So, we have corresponding y component is 0. So, then equation of continuity enforces that u is only function of y, and you have the x momentum, and y momentum indicates that pressure is a function of x alone. So, this is more or less in line with what we have discussed for clear flow channel case. Now, let us look at the porous region. Okay. So, this is just before that quick look at conclusion that dp dx is constant. So, this number of times we have discussed. Okay. So, now porous region, again if you simplify, we get this is function of y and this is function of x. So, again the corresponding pressure is constant. Okay. So, we have a unidirectional assumption both in clear flow region as well as a porous region. So, in both cases we have, and in both cases we have got the corresponding inference that the pressure, individual pressures are constants, pressure gradients are constants. Okay. So, we are now assuming a flow driven by constant pressure gradient, and then how the interface phenomena controls the total volume flow, etcetera, we are going to analyze. Okay. Okay. So, this is a major assumption. I will come back to this. Okay. So, I will speak little bit on what could be the scenario if this is not the case, that is if mu effective is not equals to mu. Okay. So, then the flow in both the layers is driven by the same pressure gradient. So, we are assuming this is a common pressure gradient. Okay. So, there could be deviations here, like somebody may try to take a averaging and then define a average pressure gradient, okay, but that will not change the qualitative behavior much. So, in particular when we are doing non-dimensionalization, so the corresponding velocity profiles, etcetera. So, they remain very much same. Okay. So, we go for this assumption, and setting up the boundary conditions, no slip at the upper wall. So, upper wall is a clear flow, therefore, corresponding U f is 0, and at the interface, say in the previous lectures we discussed about the interface conditions, in particular this being unidirectional and it is a Stokes-Brinkman coupling. So, we have the corresponding interface conditions. So, this is a continuity of velocity and a continuity of the stress at the interface. Okay. So, then no slip condition at the bottom. So, if you see the bottom is a porous packing. So, therefore, the corresponding U p is 0. Okay. So, what we should make a note is, so this is our configuration. So, this is porous. So, here U f is 0 and here U p is 0, and then we have an interaction of U f with U p. So, here we are using interface condition. Okay. So, we would concentrate more on what is happening by virtue of these coupling conditions. Okay. So, this is the complete boundary value problem, but if you see as such the equations are independently can be solved, because see this can be solved and similarly this can be solved, but you would expect from the previous lecture you can guess there will be 2 arbitrary constants involved in this solution, and similarly there will be 2 arbitrary constants involved if you get the solution of this, and total we expect 4 arbitrary constants, and then we have 4 boundary conditions. You see 1 above, 1 below, and then 2 at the interface. So, the problem is pretty much well posed, and then one can attempt for the solution. So, the mean velocity is defined. So, here see minus h to 0 is porous and then 0 to h is the fluid. So, correspondingly we are taking the corresponding velocity and then we are integrating and we are normalizing by the total width, that is 2 h. So, that is the definition of mean velocity here. Okay. So, usual non-dimensionalization. So, here for both the porous and fluid velocities we are using the one characteristic velocity, and similarly for pressure also we are using the same, and here only one length scale, that is a h as the length scale. So, that is used. Okay. So, we non-dimensionalize, and once you non-dimensionalize you get such simple structure. We have already seen what is the definition of alpha square. So, that is on our Darcy number. Okay. So, with this we are defining already we have indicated we have a constant pressure gradient in each region, it is the same. So, this should be one of them should be f there. So, any case both are equal. Okay. So, non-dimensionalized boundary conditions. So, we got so earlier we had mu effective equals to mu, that assumption has killed. So, it is making it independent of the viscosity, but if one would take otherwise, so then we get a viscosity ratio here. Okay. So, any case throughout the analysis we are assuming both are equal. So, once we have the corresponding non-dimensionalization, we have the corresponding volumetric flow rate balance in this form. Okay. So, as I indicated, we get two arbitrary constants d 1 and d 2 for the fluid region, and for the porous region we have two arbitrary constants. And already for unidirectional fully porous channel we have seen the solution depends on the Darcy number or alpha, and we get hyperbolic functions. So, corresponding solution is given. So, we have to eliminate d 1, d 2, c 1, c 2, this should have been superscript. Okay. So, subscript that is fine. So, d 1, d 2 we have to eliminate. So, these are the constants we have to eliminate. So, it is straightforward. So, I am not giving you the algebra, because I think if really one would like to at the end of this course, if you would like to get on to a research level and then start taking up some research problems, it is better that you work out this algebra and then get these values, so that you feel for yourself, because working out these algebra is really very routine. Okay. So, you will not get so much of fun if I do the algebra here in the lecture. So, it is better for you, you do the algebra and then get the agreement with the algebraic expressions whatever is obtained. So, then you feel confident really what is happening both physically and mathematically. So, then you will be ready to take up some research problem. Okay. So, this is the structure, and as you can see the pressure gradient is sitting very much, and we balance the volumetric flow rate and then eliminate the pressure gradient, determine the pressure gradient. Okay. So, this is again straightforward. So, now let us see some results. You see, so we have an interface at y equal to 0. Okay. So, for this configuration what is happening is the following. So, you have this is the porous. Okay. So, in fully clear flow we have seen the profile is this maximum at the center. So, now what is happening? So, suppose you slowly introduce some particles, then what happens? Naturally the flow which is supposed to come completely, there is no space, okay, because some space is occupied by particles. So, it something comes out, but then due to resistance, so some only can go. Okay. So, the total volume flow has to be adjusted. So, it will come like this. So, that is what will happen in this case. So, in this case what you expect is, we expect for no porous, no slip, but there is some percolation happening here. So, it is not completely no slip exactly symmetric, but some flow percolates. Okay. So, that is what we expect, and of course, this depends on the porous packing, how it is, right. So, if it is fully porous, fully no porous material, you get, you see this is no slip here and here, but since part of it is porous. So, here it is no slip, but here it is dragged because some flow is percolated inside. Okay. So, that is what is happening. So, you can see for a particular, so this case let us analyze this is nothing but large Darcy, that means it is almost equivalent to the clear flow. That means, from -1 to 1 there is no obstruction, therefore, it is a completely clear flow channel. So, you have no slip here and here. Okay. Now, let us say reduced Darcy. So, it is large Darcy, then you are reducing the Darcy number, that means resistance is more. So, once resistance is more in this bottom, so then what you expect is the total volume flux whatever is coming, that will be reduced. So, and that is being adjusted here in the clear flow channel. Further you reduce the Darcy number, it is further the velocity is less and that is being adjusted in the clear flow channel. Further the Darcy number is very low, that means whatever volume flux coming, that has to be completely adjusted in the upper clear flow region. Therefore, you have such large velocities and very small within the porous region because of the low permeability. Okay. So, this is at the boundary. Okay. So, that is what is happening at the boundary. You can see this is this crossovers happening, okay, because of the adjustment. Then already this is the onset of clear flow solution. So, if you superimpose clear flow solution, it is agreeing very much. Okay. So, this is a partially filled channel. So, the momentum exchange happening by virtue of the permeability. If the permeability is large, so then you will not see the impact of the interface so much, that is what you have seen. If the permeability is decreasing, then you will see the impact of the interface very much. As I indicated, the impact of the interface is seen, you see from here it is reducing, and if for low permeability is further. Okay. So, this is a net analysis of this. So, now in the last in the first lecture of introduction to porous media, we discussed about various boundary conditions, and we briefly discussed about something called a stress jump condition. Okay. Well, if you recall, we discussed that the exact set of interface conditions is not settled yet. So, there are some universally accepted models and then people are using. So, most recent is the stress jump boundary condition, which is proposed by Tapia. So, correspondingly there will be a jump in the tangential stress. Okay. So, what we thought is the similar problem whatever we discussed right now, we will slightly change the boundary condition. Setup is same, except that we introduce this stress jump boundary condition and then get some additional insights. So, correspondingly, so these results already I have explained. So, what we talk is on the interface we change, instead of continuity of stresses, we use the stress jump condition. Okay. So, that means the configuration is again the same. Here UF is 0, here UP is 0, and here UF equals to UP is one of the condition. Then the other condition is what is written. So, this must be equals to beta by root k mu u p. Okay. And this beta is called stress jump coefficient. Okay. So, this was introduced in 1995 by Tapia. Correspondingly, lot of literature has come following this interface condition. Okay. And in the pioneering work by Tapia, when this was introduced, it was indicated that this beta can be of order 1, it can be positive or negative, but consequently there were some corrections to the initial statements made by Achatapya. Okay. So, before we go to more details, so let us see how this stress jump coefficient play a role. So, if you non-dimensionalize, again we are repeatedly assuming mu effective equals to mu. Okay. So, otherwise what happens, I will talk a little while later. So, this is a non-dimensionalized stress jump condition. So, naturally if beta equals to 0, we retain the continuity of the stresses. Okay. If beta is non-zero, so we can get various scenarios. So, now the corresponding solution is obtained. So, as you can see, this time the coefficients are not only functions of alpha, that is indirectly Darcy number, they are also functions of the stress jump coefficient. Okay. So, the pressure again as usual can be pressure gradient can be estimated. Okay. So, let us look at the analysis. Okay. So, here if you see, beta controls in some sense the momentum transfer across the boundary. Okay. So, for large beta at the interface, because this is the role of beta is more prevalent at the interface. So, for large beta at the interface, you can see the momentum transfer is more. So, therefore, you have high velocities. Okay. So, here velocity is low. Okay. So, compared to this beta, but here at the interface these are other way. Okay. So, for large beta the momentum transfer is more at the interface, and you can see a thin boundary layer kind of behavior. So, when I say boundary layer, so please do not worry that we have not yet discussed the exact definition, etc. What I am trying to say is symmetric some thickness. So, within this the interface phenomena is more active. Okay. So, whatever the role of beta, it is more active within this. So, here it is roughly some 0.3 kind of. So, there is one crossover and second crossover. So, y equal to 0 is the interface. Okay. So, the momentum exchange is more prevalent within this strip of the around the boundary. Okay. And the usual volume flow adjustment is taking place here as well. Okay. Because below is porous and then above is clear flow, but this is for a particular particular Darcy number. Okay. And this is varying stress jump coefficient. So, you can see for beta is 0.7, the velocity in the clear flow is less, but then it is getting increased, and then after crossover to meet the corresponding no slip condition, again it is reduced. Okay. So, if beta is 0, you get the continuity of the stresses, and then the solution agrees very much with the partially filled porous channel with the continuous stresses. So, that is happening. So, now since I talked so much about the effective viscosity, etc. So, this typically this is a relation used initially by Achatapya. Okay. (1995). So, Achatapya and Whittaker have used. So, this is Stephen Whittaker. So, these two have used volume averaging approach and then introduced the stress jump condition. So, there they have used this correlation. So, where phi is the porosity. Okay. But there are various other correlations, relation between effective viscosity and the viscosity and relating porosity. So, depending on the context and then depending on the purpose, people use various formulas, but the pioneering work by Achatapya, once it is introduced, a lot of literature has come using this particular correlation. Okay. So, in particular when people are using heat transfer problems in porous media, So, there is a lot of literature considering stress jump and its impact. So, those who are interested in heat transfer literature, so they can pay attention to the work of Achatapya and then work of Kuznetsov, where this stress jump condition is used. So, this gives some insight of composite filled porous channels and then the corresponding agreements to clear flow channel, etcetera. But I said there are more interesting applications given by, suppose you have a layer of thickness, porous layer. Okay. So, this is porous coating, this is porous. So, we are talking about a tube. So, inside it is a free flow. Okay. So, these kind of applications have more use, because these are more close to various arteries, flow inside glycocalyx layers, etcetera. So, maybe in coming lectures we will discuss some of these. Okay. So, hope you get some idea about the overall how the momentum transfer occurs when you have an interface, and then the corresponding role of the stress jump coefficient, etcetera. And we look forward for further applications. Thank you.